We have defined intrinsic carrier concentration while discussing intrinsic semiconductor in our previous videos. In this video, we're going to understand Ni in more detail. In the sense, we'll understand the mathematical equation for it, and we will understand what Ni depends on. The number of electrons per unit volume, which usually we will take as centimeter cube, which is called the electron concentration in conduction band, we called it as N. And similarly, the number of holes per centimeter cube, which is per unit volume, in valence band is given by P. We know that in intrinsic semiconductor, the number of electrons in conduction band is equal to the number of holes in valence band. So we can say the carrier concentration in conduction band, which is N, will be equal to the carrier concentration, which is the hole concentration in valence band. So we can write for intrinsic semiconductor, N is equal to P. So we defined this to be equal to Ni, where Ni is actually the carrier concentration in intrinsic semiconductor, which doesn't tell if it is electron or hole because both are same. So we're going to say Ni is the intrinsic carrier concentration. Concentration means number per centimeter cube or number per volume. We have seen and derived in previous videos that electron concentration in conduction band is given by Nc times e power minus of Ec minus Ef over Kt, where K is the Boltzmann constant and Ec is the bottom edge of conduction band, Ef is the Fermi energy level, and Nc is the effective density of states in conduction band. And we also derived for the hole concentration in valence band, which was given by Nv, which is the effective density of states in valence band, times e power minus of Ef minus Ev over Kt. And Ev is the top edge of the valence band. And now to find what is Ni, we can take N times P is equal to Ni square. Then we can write this as Nc times e power minus of Ec minus Ef over Kt times Nv times e power minus of Ef minus Ev over Kt. And this is equal to Ni square. So we can write Ni square as is equal to Nc times Nv times the exponential. I'm going to add the terms here. Ec minus Ef plus Ef minus Ev over Kt, where minus Ef and plus Ef cancel. So we are left with Ni square is equal to Nc times Nv times e power minus of Ec minus Ev by Kt. So Ec minus Ev is nothing but Eg. We have seen this, which we defined as forbidden energy gap, which is Eg over Kt. To just show you the terms Ec, Ev, and Eg in the energy band gap, I'm just taking the energy band gap here, where we called this the conduction band and the bottom band as valence band. And we said the top edge of the valence band is Ev and the bottom edge of the conduction band is Ec. And we defined Ec minus Ev difference as the forbidden energy gap Eg. Now we have Ni square value. Now let us find what is Ni. Ni is equal to square root of Nc Nv times e power minus Eg over 2Kt. While deriving the expressions for N and P, we found out the values of Nc and Nv as well. So we know what is Nc, which is given by 2 times 2 pi Kt times the effective mass of electron over h square whole power 3 by 2. And we also know what is Nv, which is given by 2 times 2 pi Kt m h star, which is the effective mass of hole over h square whole power 3 by 2. If we substitute these values of Nc and Nv to find the value of Ni, we can write this equals to 2 times 2 pi Kt over h square whole power 3 by 2 times the effective mass of electron times effective mass of hole power 3 power 4, because it is in the square root, And here these terms are present twice, so square root of it gets cancelled. We get exactly the same value times e power minus eg over 2 kt. I have written the expression here for Ni. Now we can still further rewrite this to separate the terms in terms of temperature dependent versus temperature independent. Now these terms are like independent of temperature, so I'm going to take Ni is equal to this to be some constant. I'm picking a constant a times t power 3 by 2 times e power minus eg over 2 kt. Sorry, here we should be having 2. Now we can see that Ni is depending on temperature here and here. And in fact, if you remember, the energy band gap also was depending on temperature, because energy band gap depends on the intraatomic distance, and intraatomic distance of a material depends on temperature. And we have seen in general, when temperature increases, intraatomic distance increases, so energy band gap decreases. So in the sense, we can see from this that Ni is a strong function of temperature. In fact, one of the term is exponential. So it's a very strong function of temperature. And another thing to note is A is a constant that depends on the effective mass of electron and hole, and rest all are constants, the K and H, Boltzmann constant and Planck's constant. So which means the effective mass of electron and hole is something that is characteristic of the material itself, which means A depends on material, and the Eg basically is also dependent on material. In the sense, what material you're picking. Let's say for silicon, the Eg is 1.1 electron volt at room temperature. And for germanium, it was 0.66. So basically, Eg depends on the material. And of course, it depends on temperature as well. So in the sense, we can say Ni is a strong function of the kind of material you're picking and the temperature as well. I'm taking some examples to show you the importance of the energy band gap for a semiconductor. At room temperature, which is 300 Kelvin, which is 27 degrees centigrade. I'm going to take it for 3 different materials. One, germanium, second, silicon, and third, a compound semiconductor, gallium arsenide. So for this one, I'm just going to write the energy band gap at room temperature and the intrinsic carrier concentration Ni. So for germanium, energy band gap is 0.66 electron volts. Let's say Eg is written in electron volts. And for silicon, this is 1.11 electron volts. And for gallium arsenide, this is 1.43 electron volts. And if you see the Ni value for them, for germanium, it is 2.5 times 10 power 13. So the units is number per centimeter cube, which is number per unit volume. And for silicon, this is 1.5 times 10 power 10. And for gallium arsenide, it is 2 times 10 power 6. Of course, here we're looking only at Eg, but of course there is a term A which also depends on material. But let's concentrate only on Eg for now. As Eg is increasing, the energy band gap is increasing, the Ni, the intrinsic carrier concentration, is decreasing rapidly at the same temperature of comparison. We will see in future where the leakage power or leakage current of a diode depends on Ni. So if Ni is higher, the leakage current is higher, which means leakage power will be higher. So the smaller the Ni, the better it is in terms of leakage power. We'll see this and analyze in more detail when we actually discuss the p-n junction diode. This is a material to watch out because most of the problems in this course will be based on silicon.